Hello, hello world. So today we are going to solve another interesting problem that has been, according to the daily codings, that it's recently appeared in Google on-site interview. There's the problem number is daily coding 1022. That means 1022nd. So let's read that problem statement and we will work through it. So here is the problem statement. Please read it. I'm going to summarize. So you have given an array. In that array, every number has been repeated 3 times except one number. That number repeated only 1 time. So we need to find out that number which appeared only 1 time. So let's look into that array. In that array, if you see that 6 has been appeared 1 times, 2 times, 3 times, and 3 has been appeared 1 times, 2 times, 3 times, and only 1 has been appeared in 1 times. So it sounds like pretty straightforward problem. You can do even some basic mathematics to find each of these individual number like a set or unique distinct number and sum it, multiply with 3 times, and then add existing all the array elements, subtract and divided by 2. That will give you a solution, but we will do little better even with the naive approach. All right, and the goal to solve this problem is in big O of n time. So that's where the complexity will arise, but let's work through first, start with the naive approach. So in this naive approach, what we are going to do is we will count each of this number, how many times it has been appeared. If we can count, let's say in our array example, 6 has been appeared 3 times, and then, sorry, let's do a little better. Okay, so 6 has been appeared 3 times, and 3 has been appeared 3 times, and 1 has been appeared 1 times. So if we could do that, and then we will just look into that which number has been appeared 1 times, and we can return that value. That solves the problem, right? So let's do that. So in that case, we need a counter, right? So integer, we will name it counter equals to new hash map. We need an hash map. Oh, all right, interesting. Okay, sorry about it. Okay. All right, so now we need to go through each of this number. So let's go through each of this number, integer num, into our array. And then what are we gonna do? We'll say counter dot compute, and our key is number, and then it will return a key and value, and we'll check if b is equal null. That means this is the first time that number has been appeared. In that case, it will return we'll say 1, or else b plus 1. So if it is the first time, if it is empty, it will give you the 1, or else it will check that what is the existing value, add 1. So pretty straightforward. Now we get the counter. Now in that map, we need to iterate through that map and then return the value. So let's do that. To iterate through the map, you can say map.entry. Entry, in that entry object, what we have, integer and integer. All right, so we will call it entry, and then we will call counter dot entry set. All right, so looks good. Now if entry dot get value is equal 1, because we counted, if the value is 1, what are you gonna do? Return we'll say entry dot get key, because we need to return the key. So that should solve the problem. So otherwise, if it doesn't exist or something, we can return -1 or something. That's fine. So let's run it, see what happens. Wow, 1, right? So 1 has been appeared 1 times, which we get the expected result. Fine. Now what is the problem with that? The problem is that memory, right? The time complexity, TC, let's do a little more exercise here. Time complexity, because we need to iterate over each of this element. So it's big O of n, which is linear time. What about the space complexity, right? Space complexity is we have used an extra data structure, which is an hash map. It's storing each of these numbers. So we will say another big O of n space, but we don't want this. We want something constant space, meaning what is the constant space? Meaning that whatever the data size is, that memory you have allocated, it's not gonna change. It's always constant. So that's the interesting part of this problem. So I was not even able to directly come up with the solution thanks to one of my friend and brother. His name is Sadek. Thanks to Sadek for helping on come up with a very elegant solution. So let me go through those. So this is our naive implementation. We will do now a little better. Let's do that. We'll say find missing number instead of naive. We will say, let's say optimal, right? Optimal solution. We'll pass this array. Create this method, right? We will return an integer from here. Let's keep it -1. Okay. So now we need to make a very cool observation. Let's start with an example, very simple example. All right. So let's say that the number we have 1, 1, 1, 2. All right. So if you look into the bit representation of those number, look what happened. So how you represent 1 in binary? So 0, 0, 1. So the next one 0, 0, 1. Another one 0, 0, 1. And then the next two is 0, 1, 0. If you see that each of this column, look at here, how many times 1 has been appeared here? 3 times. How many times 1 has been appeared here? Only 1 times, right? So if we summarize why it works, we will go there. So here that 1, it doesn't have any 1, so we'll say append 0 because 0 divided by or 3 remainder will be 0. Here the second column, number of 1 has been appeared 1 time, so 1 divided by 3 remainder would be 1. And what about here? 3 times, so 3 divided by 3 remainder is 0. Now this is actually the value of 2, so 2 is the missing number. The reason is each of this number has been repeated 3 times. That means if you represent this into a binary string, each of these bit value or the position, it could be MSB, LSB, whatever, in that position has to be 1, has to be repeated 3 times because that number has been repeated 3 times. If another number has been repeated 3 times for maybe another location has to be repeated 3 times, so 3 plus 3, 6 times. So it will be always a multiple of 3, except the number what is missing. For that number in some location, it will not be multiple of 3. So we will take that remainder actually as a key. Hope that makes sense. So let's start. So what are we going to do is, we know that since this array is an positive integer, any positive integer in Java we can represent into 32-bit, okay, because 2 to the power 31 is our maximum integer value. So let's do that. Okay, so we'll say bit count, right, teacher 31. All right, now for each of this number we need to do few things. We need to find out the representation of that number into 32-bit string, right? So that would be easier to make operations. So num array, so now we have the number. Now this number has to be represented into a 32-bit, but the problem is if this number is 1 in Java, if you say okay, I need integer parts dot to binary string, it will immediately return only 1 bit. So that's what we don't want. We want into a 32-bit string. So what we could do is, let's say we'll call temp and 1, and then if you left shift 1, into 31 bit. So what it will happen, so let's say instead of these two, general representation of 1 is 1, now you have to move it to the left shift, right? So if you left shift, you just append 0 and 0. Cool. So that's just basically append that. Okay, so we are going to do it 31 bit. So now it's basically it's a binary string with 1 and then 30 zeros. Sorry, 31 zeros. So that total length will be 32. Now we have this number, that number and this temporary string. If we do an operation like AND operation, OR operation, in that case what it will left over is that only that number, right? So we are going to do that. Okay, so we will do an experiment what exactly happened. So let's do a binary string, or let's say we'll say that concatenate binary string or binary number, probably let's say binary number. Okay, so temp, and then we'll do an OR operation with the num. So that should give us a number. If you convert it into a string, that should be 32 bit. So let's do that, see what it gives us. So integer dot parse now to string, and you'll say that binary number. If we print it, see what happened. Run that code. Okay, look at that. So 1, because we moved that left shift we did, and then when we did an OR operations, this is the number, right? Our first number was what? 6, right? This is the representation of 6. So do that. And only problem is there is an extra 1, and this length of this string is 32. So that means we can actually discard the first bit, most significant bit. What we can do here is that we'll say string, change string, and also binary string, integer dot to binary string, then binary number dot substring, and we'll say 1. So from the first position it will give us so it will basically discard this, the first most significant bit, and it will left over with this. So let's print it and see that it's actually doing what it's supposed to do. Okay, no, it's not. Binary string, now print it. So what is happening here? Yep, so if you print, you see that except the original number, it just appended a bunch of zeros, nothing else. Now since we have this number represented into 31-bit string, basically we are going to check each of this column and count, right? So what are we going to do is something like this: integer, no, character C, binary string dot to character array. So now it becomes a character array with 0 and 1, and then what we are going to do each time when we hit an 1, we will go to this bit count and we'll update, we'll count that for this position or for this column 1 has been increased. So let's do that. In that case, if C equal 1, what are we going to do? We are going to say bit count. We need a position, all right? Let's say position. This position has to be increased because for the next position, and then plus equals to bit count. We don't need that 1. So whatever it has in that bit count dot position, it will just append 1. So what is that position? We don't know. Let's do that. Position start with 0. So it will start from the 0th position. It will start building that column. So in this case, if we think about like 3-bit, let's say instead of 31-bit, we'll say 3-bit, 1 1 0. So first character it will say 1. So it will say 1, and bit count position, what it will happen is, so let's say this is our bit count, it will check in that position, bit count position, current value is 0, it will append 1. So 1, and then it will go to the next position. For the next position, character is 1, so it will again 1, and then next position is 0, so it's 0. So after, what is our next number? 6 and then 1, right? So the binary representation of 1 is 0, 0, 1. So start with that. 0th position, it will not increase the counter, and then this position, it will not increase the counter, and then for this position, it will not increase the it will increase the counter, so 0 will be 1. So ultimately, for after full operation of with all of this number, this bit count array will be changed. Okay, we'll print it and see what happened here. If it is else, for the 0, do we need to do anything? Probably no. Let's just print it, see what happened in our bit count array, right? Integer I equals to 0, I less than 31, because 31 bit, I plus plus, and then we'll see how it counts, right? All right, bit count of I. Okay, I'll just give something so that it will be printing. Okay, so now if I print it, let's see what happened. Okay, I'm not gonna print that, it will be so much messy. So if you do that, okay, it's too big, right? Yeah, because of this gap. So let's remove that for better understanding, right? So look at that, for each of this number, what it did, right? What happened here? We got this binary string, bit count, and then one of the things we missed here is that the position, we need to increase this position, we increase it, and we need to check another as well. So if that bit count, so position plus plus is equals plus equals 0, so that even if the problem was that whenever it was 1, it was updating the position, but when it was 0, it was never did. So that position was like at the beginning in the MSB side was increasing. So now it should be fine. So let's print it. Okay, so looks good, right? All right. Okay, so in that case, if we just take it out from this for loop, print it here, so that it will give like a single value with the count. So look at this. So it counted 4, 6, and 3, right? This is the return value. Okay, so it's counted, isn't it? 3, 6, and 3. So now we know that what is the count. Each of this column, we need to find that the remainder by 3. Now we need to build the result as well. How are we going to do that? Let's create a string builder SB, or we can say result string SULT, right? Okay, so I'm not cutting this video in any second and making this little mistake here and there. It makes more human, that's what I feel. Otherwise I could write the code before, copy and paste it, but it will be not more like human, right? So I think that's more better actually. So we have that. Now what we are going to do is this result string, we will append, we'll say, what was that name, bit count of this column, ith column, and we'll say ampersand 3. So it will give us the remainder. If that remainder is 1, it will append 1. If it is 0, it will append 0. So okay, so we will get this result string. Let's print that. Okay, so this is the result string. Voila, it looks good, right? All those zeros, only 1. Our number was 1, was only missing, correct? What we are going to do is we'll returning integer dot parse integer result string dot toString, and we have to give 2 because it's a binary. We need to a binary string to integer. So if we run that, see what happens. Voila, it worked. So let's give another example. Instead of this, let's give another example. Could be this one, right? 13, 19, 13, 13. Looks good. Let's get there. Let's see what it gives. Woohoo! It gives 19. So it's all good. Now, what about this approach? What is the time complexity and the space complexity, right? So space complexity, what we are doing is we are just storing this all the count in a bit count array. So in that case, the space complexity will be big O of what? 32. We can say it's a constant, right? It's never gonna change for any number of element we have. Doesn't matter. So we'll say constant. CONS, constant space, right? Expected. Now, what about that time complexity? So first of all, we are going through each of this number. If there is an n number, it will give you big O of n, right? All right. Plus, each of this number, they have 32-bit. We need to process each of these 32-bit. In that case, there will be for each number, n number, it will do extra 32 operation, n times 32, which is equivalent to, again, in big O notation, it's big O of n. Right? Sweet. That's about it. Okay, their code could be optimized in a lot of places, but I try to make it easier that anybody can understand, and at least in one shot, you can understand the problem, what happened. Okay, so for this solution, I especially thanks to that brother, Sadek. Thank you, Sadek, and thank you, everyone.